Hello students, welcome to the next section of connectedness in topological space. Okay, we will start with the theorem. This theorem says that let X be a topological space, then the following are equivalent statements. In the previous class, we discussed some equivalent conditions for disconnectedness. Here, we will discuss equivalent conditions for connectedness. The first statement says X is connected. Second one, X cannot be written as disjoint union of two non-empty closed subsets. Third one, the only Kloppen subsets of X are empty set and holds X itself. Fourth one, every non-empty proper subset of X has a non-empty boundary. Fifth one, X cannot be written as the disjoint union of two non-empty open sets. Okay. So we will prove the first statement implies second one. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 1. This theorem is actually the negation statement of the previous theorem. So which is easily can proved. Okay. So to prove 1 implies 2, I will prove negation 2 implies negation 1. You know, P implies Q is equivalent to negation Q implies negation 1. So to prove this statement, we need only prove this one. We prove negation 2 implies negation 1. What is negation 2? Negation 2 means negation statement of the second one. X cannot be written as disjoint union of two non-empty closed sets. രണ്ട് non-empty closed സെറ്റുകളുടെ യൂണിയൻ ആയിട്ട് എക്സിനെ എഴുതാൻ പറ്റില്ല എന്നാണ് സെക്കൻഡ് സ്റ്റേറ്റ്മെന്റ്. Negation means X can be written as, which implies, so let X can be written disjoint union of two non-empty closed sets. Okay, so that is X is equal to, I take A union B, comma, where A intersection B equal to empty, which means A and B are disjoint, and an extra condition, they are non-empty closed sets. A is non-empty, B is non-empty, comma, A comma B are closed. So this is our assumption. Okay. Now we want to prove that negation 1. What is negation 1? X is connected. So negation X is connected is the first statement. Negation of 1 means X is not connected. We want X is not connected. For that, when a set is not connected means it can be written as, by definition, it is not connected means it can be written as disjoint union of two sets A and B such that A closure intersection B closure equal to empty, which is a definition of disconnected set. Okay. So I can write from here, what is A closure intersection B closure? We know A and B are closed sets. So what is A closure? A. What is B closure? B. So this is nothing but A intersection B. But we assume that A intersection B equal to empty. So you get A closure intersection B closure equal to empty. Which means X can be written A union B where A and B are non-empty sets such that A closure intersection B closure equal to empty, which by definition which says that X is disconnected. രണ്ട് സെറ്റുകളുടെ യൂണിയനായിട്ട് നോൺ എംപ്റ്റി സെപ്പറേറ്റഡ് സെറ്റുകളുടെ യൂണിയനായിട്ട് ഒരു സെറ്റിനെ റെപ്രസെൻറ്റ് ചെയ്യാൻ കഴിഞ്ഞാൽ അത് ഡിസ്കണക്റ്റഡ് ആണ്. കഴിഞ്ഞില്ല എങ്കിലാണ് നമ്മളതിനെ കണക്റ്റഡ് എന്ന് പറയുന്നത്. വേർതിരിക്കാൻ പറ്റില്ലെങ്കിലല്ലേ അത് കണക്റ്റഡ് ആവുക. പറ്റുമെങ്കിൽ ദാറ്റ് വിൽ ബി ഡിസ്കണക്റ്റഡ്. ഓക്കെ, so you get X is disconnected, which implies negation 1 will be true. So you proved when negation 2 is true, negation 1 is also true. So negation 2 implies negation 1 will be proved. It is proved. Therefore, we proved 1 implies 2 is true. Okay. Similar way, we can prove that 2 implies 3. What is 2 implies 3? For that, we prove negation 3 implies negation 2. Okay. I will prove negation 3 implies negation 2. What is negation 3? 3 says that the only Kloppen subsets of X are empty set and X. Negation means the Kloppen sets is not empty and capital X. There may be a proper subset A which is also Kloppen. Okay. So I take if there exists a proper Kloppen subset A of capital X. 3 says that the only Kloppen sets are empty set and whole set. But for the negation statement, I take an extra set which is a proper subset of X, which is Kloppen. Okay, this is his negation statement. Okay, such that now we want to prove that negation of second one. That means X can be written as disjoint union of two non-empty closed subsets. Okay. So for that I choose we have A here. A is a non-empty proper Kloppen subset. Now take B is equal to its complement X minus A. Since A is closed, X minus A can be considered as open, or since A is open, X minus A be considered as a closed set. Okay, since A is Kloppen means both closed and open. You consider A is open. When A is open, X minus A will be closed. Its complement will be closed. Okay, what is X minus A? It is B, right? Which means B is closed. So we get A is also closed set and B is also closed sets. Since A is Kloppen, it can be considered as closed also, which implies A and B are closed sets. Now, if we prove capital X is equal to A union B and A intersection B equal to empty, that will be the negation of the second statement. If capital X is equal to A union B, A and B are closed sets, okay, and A intersection B equal to empty means it is disjoint also. So that will be the negation for this second statement. Okay. So we have A is closed, B is equal to X minus A and B is also closed. Okay. And what is capital X? I can prove that this capital X is A union B because we have A is a proper subset of capital X and B is equal to X minus A. Okay. So which means what is A union B? A union B is nothing but a subset of X union its complement. This is nothing but capital X itself. Okay. Now what is A intersection B? A intersection B is nothing but A intersection B is taken as X minus A. So A intersection X minus A which is equal to B. Which means X is equal to A union B. X can be written union of two sets where A and B are disjoint because its intersection is empty, disjoint closed sets in X. So A can be written as disjoint union of two closed sets A and B, which means the negation 2 statement is true. So you proved negation 3 implies negation 2, therefore 2 implies 3 will be proved. Now 3 implies 4. How will you prove 3 implies 4? In a similar way, negation 4 implies negation 3. So what is negation 4? Negation 4 says that the fourth statement says that the only Kloppen sets in capital X are empty set and full set. Negation means there exists a proper Kloppen set. Proper Kloppen. That means which is not equal to empty and which is not equal to capital X. അത് രണ്ടുമല്ലാത്ത ഒരു പ്രോപ്പർ ആയിട്ടുള്ള Kloppen sets ഉണ്ട് എന്നാണ് ഞാൻ എടുക്കുന്നത്. That will be the negation. Okay. So there exists a proper Kloppen subset A of X. We want negation 3. I'm sorry, this is not the fourth statement. Fourth statement says that every non-empty proper subset of X has a non-empty boundary. What is the fourth statement? Fourth statement says that every non-empty proper subset of X has non-empty boundary. That means for every A subset of which is proper ana, A proper subset of X comma del of A equal to not equal to empty. This is the fourth statement. We want to assume its negation. What will be its negation? For every A proper subset of X, the boundary of A equal to non-empty means its negation is there exists a proper subset A of X such that del of A equal to empty. It is the negation of fourth statement. Clear? It is the negation of fourth statement. Idana fourth statement. Okay, this is the fourth statement. In mathematics, I can write for every A in proper subset of X, del of A not equal to empty, which means its negation means there is a proper subset A of X such that its boundary is empty. What is we want to prove? Negation 3. What is negation 3? The third statement says that the only Kloppen sets are empty and capital X. Only Kloppen means both closed and open. ക്ലോസ്ഡും ഓപ്പണും ആയിട്ടുള്ള സെറ്റുകൾ എം ടി സെറ്റും എക്സും മാത്രമേ ഉള്ളൂ എന്നാണ് തേർഡ് സ്റ്റേറ്റ്മെൻറ്റ് പറയുന്നത്. സോ വാട്ട് വിൽ ബി ഇറ്റ്സ് negation we want to prove, we have to prove that negation 3, that is the only Kloppen sets are empty and X. Negation will be there exists a proper subset A of X such that A is Kloppen. 5ഉം എക്സും അല്ലാതെ ഇത് രണ്ടും അല്ലെങ്കിൽ ഏതാ, ദാറ്റ് വിൽ ബി പ്രോപ്പർ സബ്സെറ്റ് ആയിരിക്കും. അപ്പോൾ അങ്ങനെയുള്ളൊരു പ്രോപ്പർ സബ്സെറ്റ് ഉണ്ട് ക്യാപിറ്റൽ എക്സിന്. എന്ത് പ്രോപ്പർട്ടി കൂടെ വേണം? ക്ലോപ്പൺനെസ് വേണം. സോ വി വാണ്ട് ടു പ്രൂവ് ദാറ്റ് ദർ ഈസ് എ പ്രോപ്പർ സബ്സെറ്റ് A of X such that A is Kloppen. There is a proper Kloppen subset of capital X. This is we need to prove. Okay. So we assume negation 4 is there is a proper subset A of X such that del of A equal to empty. So now take let B equal to X minus A. When you take B equal to X minus A, and we have boundary of A equal to empty, which means I can prove that what is boundary? By the definition, boundary of A equal to empty means A closure intersection X minus A whole closure is equal to empty. Then by previous theorem I can write, which implies X minus A whole closure is contained in X minus A closure. This will be contained in complement of this, and this will be contained in X minus A. X minus A closure is always contained in X minus A. So which implies X minus A closure is contained in X minus A. Also we have X minus A is always contained in X minus A whole closure. So from here I can write X minus A closure equal to X minus A, which implies a set is equal to its closure means X minus A is closed, which implies A is open. Okay, this is also proved in the previous theorem. Similarly, del of A equal to empty means A closure intersection X minus A whole closure equal to empty, which means A closure will be contained in X minus A whole closure. This will be contained in complement of this. Okay, so which will be contained in X minus A? It is nothing but capital A, which implies A closure is contained in A. We already know A is always contained in A closure. Okay, we have this. We know A is always contained in A closure. From this and this I can write A equal to A closure, which means A is closed. When A is closed, X minus A is open. And what is X minus A? B. B is taken as X minus A. So you get B is open. So when del of A equal to empty, and if you choose B equal to x minus A, using the definition, I can say that A and B are open. So which implies we assumed that A is open. We have assumed that there is a proper subset A of x such that del of A equal to empty. When del of A equal to empty, I can prove that A is open and A is closed. I proved that A is open and A is closed. So which means A is both open and closed, which means A is open in X. Open in X. So what is A? A is nothing but a proper subset of capital X such that del of A equal to empty. A is chosen such that it is a proper subset of capital X such that del of A equal to empty. Using this assumption del of A equal to empty, we proved that A is both open and closed. That means A is closed, and which implies A is a proper open subset of X. Which implies A is a proper open subset of X, which means negation 3. 3 says that the only open sets are phi and capital X. So now you get an open set, you get a proper open subset A. So which will be the negation statement of 3. Okay. Now we will prove 4 implies phi. So we will prove negation phi implies negation 4. So what is negation phi? For that we need to know what is the fifth statement. So the fifth statement says that X cannot be written as the disjoint union of two non-empty open sets. So what will be the negation phi? So assume X can be written disjoint union of two sets A and B. Disjoint means their intersection is empty and they are open sets. A and B are open sets and A comma B are open. So this is the negation statement of fifth one. Ready? So X is equal to A union B, A intersection B equal to empty, and A and B are open. We want to prove negation 4. What is 4? Every non-empty proper subset of X has a non-empty boundary. What is the negation? There is a non-empty proper subset of X which has empty boundary. Okay, so we want to prove the negation statement. Ready? So for that I also take let B equal to X minus A. Not let, since X equal to A union B, A intersection B equal to empty always implies B will be equal to X minus A. Okay, then you find what is del A. Del A is by definition A closure intersection X minus A the whole closure, which is equal to A closure intersection. What is X minus A? X minus A equal to B. And what is A intersection, A closure intersection B? Which is clearly empty. So which means A is a proper subset of X such that del of A equal to empty, which is the negation statement of 4. So you proved 4 implies 5 is true. Now for the last one, 5 implies 1. So assume negation 1. Negation 1, we will prove negation 5. What is negation 1? 1 says that X is connected. So negation 1 means that is X is not connected or disconnected. Since X is disconnected, by definition, there exists two non-empty subsets A and B such that A union B equal to capital X and A closure intersection B closure is equal to empty. This is by definition, okay. So which means A union B equal to capital X is here, and A closure intersection B closure equal to empty means I can write A intersection B equal to empty, because A closure intersection B closure equal to empty means which are mutually separated. Mutually separated always implies mutually disjoint. Therefore, A intersection B will be empty. Then by previous theorem, there is a statement phi implies 1 will be true in the previous previous theorem. So by that theorem, A union B equal to X, A intersection B equal to empty means you can prove that A and B are open. So you get the negative statement of phi. So all the 5 statements are equivalent.